Let me start out, and I'm sure many people will be joining as we get going. I want to welcome everyone to our first of the calendar year, first distinguished lecture series of a seminar. Reminder to everybody, every month we have a distinguished lecture speaker, and then in the same month, we typically have our internal series featuring Northeastern faculty researchers called Expeditions in Experiential AI. So today, for our distinguished lecture series, I am pleased and honored to be introducing Cynthia Rudin, who is doing, who is recognized, first of all, as one of the world experts on the area of explainability and interpretable models in AI. She has had many honors, but the one that I will feature is the one that's kind of nicknamed the Nobel Prize in AI, but it's the Squirrel AI Award for Artificial Intelligence for the Benefit of Humanity, which is given by the AAAI. Cynthia is a fellow of the AAAI and of the American Statistical Association, and has been very active and played leadership roles in the optimization community, the Informs conferences, and so forth. I would like to also point out that today we'll collect questions for today's lecture as they're going on, and towards the end we have reserved time to answer your questions, and any questions we get into or we don't get to the time to present, we will handle on social media by getting answers from Professor Rudin later. Today's talk will be focused on a very interesting topic on scoring systems, which is a tool used to kind of make models more interpretable, and I am very intrigued by the fact that she's tackling them at the extreme of interpretable machine learning. There's a lot I could be saying about Cynthia and her achievements, but I really am eager to kind of turn it over. I will share one personal bit. Cynthia has been influential on my own kind of interests and research, and my hopefulness towards getting ourselves into a world where we can have AI systems that are more transparent, understandable, and acceptable. But also, I'm proud to say that my daughter was an undergrad at Duke University, actually took her course, and she was one of the forces that influenced my daughter to work on data science today at Amazon. So gratefulness from both generations on the personal side. So over to you, Cynthia. Welcome, and thank you for joining us in the first lecture of 2022.
My pleasure. And it's great to see so many familiar faces too. Okay, so let me share my screen here. Okay, cool. All right, so I'm going to talk about scoring systems today, which are really tiny little models at the extreme end of interpretable machine learning. It's really hard to believe the power of a little tiny itty bitty model. So before I talk about scoring systems, let me ask you a question, which is, can a typographical error lead to years of extra prison time? Right? This should never happen, right? Typos making decisions? That's crazy, right? Who's making a decision here, a judge or a typo? And is that fair if this happens? But it happens all the time. And this is an article about a guy called Glenn Rodriguez, who was denied parole because his COMPAS score was miscalculated. And COMPAS is a black box proprietary model for predicting future crime, and it is used in parole decisions. And yes, a typo made a decision here, not a judge, a typo, and he got years of extra prison time. Now, some definitions. A black box model is a formula that's either too complicated for any human to understand, or it's proprietary, which means we're not allowed to understand it and its inner workings. Whereas an interpretable machine learning model obeys a domain-specific set of constraints so that humans can better understand it. So it's a model that's constrained. So why do we need interpretable models? We need them when we're handling high-stakes decisions or when we need to be able to troubleshoot the model. So it's basically any time it would be really bad if the model went wrong. Because a lot of times AI models do go wrong, and they go really wrong. So what else could go wrong with a black box? Well, we already know that we could send people to prison based on typos, but what else happens? And so here I put up two of my favorite articles where black box AI models went wrong and no one was able to figure out what happened. And the article on the left, this is from a black box AI model that told everyone that air quality was fine during the wildfires and it was safe to go outside when it was not. People were seeing a layer of ash on their cars sometimes in those days. And then the article on the right is about how FDA approved AI models for healthcare are not performing as well as they should be, and no one knows why. And I've just given you a few things that have gone wrong with using black box models, but there's a tremendous amount more that could go wrong, and probably many things have gone wrong that were hidden, so I don't know about them. And now people are starting to use machine learning for all kinds of medical decision making and loan decisions and self-driving cars and all manner of other things that we really don't want to go wrong. And some people love their black boxes. They argue fiercely that they need them. Anyway, I want to get back to Compass, right? Do we really need to have black box models? Are they more accurate? Luckily, there was this data set from Florida that was released that could tell us exactly how accurate Compass is. So we have the Compass scores, along with basic criminal history information and demographic information from a few thousand people in Florida. And at the time that data was released, my lab had developed an algorithm called Corals. And Corals is a very complicated algorithm, but it produces very tiny little models. It's an algorithm for one-sided sparse decision trees, okay? So decision lists. And so we ran the Florida data through Corals, and we got a model that was so tiny that it fits on the bottom of a PowerPoint slide. And so the model looks like this, okay? It says, if the person is 19 to 20 years old and they're male, predict arrest within 2 years of their Compass score calculation. Else, if they're 21 or 22 and they have 2 to 3 prior offenses, then predict arrest within 2 years of their Compass score calculation. Else, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this model and we thought, could this possibly be as accurate as Compass? And it was. So we always do tenfold cross-validation. So you're seeing different colors from different test folds. And hopefully you can see that Compass and Corals are about equally accurate over all the different folds, test folds. And so we thought, okay, great. Let us throw the whole machine learning arsenal at the problem and see if we can get any better performance. And we couldn't. And some of these are complete black boxes, like Compass, where we don't know what's in it. This is proprietary. And some of these are very complicated models, like support vector machines with radial basis function kernels or boosted decision trees with hundreds of trees, right? You can't fit those models on a slide. The formulas would be so complicated that you couldn't do it. And on the other extreme is Corals, whose whole model is right here in the corner. So, a few years ago, there was this huge debate about the algorithmic fairness of Compass. But the truth is that we just don't seem to need Compass at all. So now you've seen that black box models are not always more accurate than simple models, but there's some more general knowledge that I need to provide you. There's really two broad kinds of problems that we encounter in machine learning and data science. There's problems with tabular data and problems with raw data. So tabular data look kind of like the criminal justice data that I just showed you, with real valued and categorical features, each of which is meaningful. This is a medical example over here. Whereas raw data are things like, images or sound waves or large amounts of text, where 1 pixel doesn't really tell you anything about what's in an image. So when these two types of data get handled differently in sort of every respect, like for raw data, the only technique that's working right now is neural networks. And, you know, that we understand. So that doesn't mean it can't be interpretable. You have to design an interpretable neural network. But even the definition of interpretability is different for sort of computer vision and those other problems anyway. Whereas for tabular data, as long as you're willing to do some minor pre-processing, all the methods tend to have similar performance, just like I showed you with the corals versus compass experiment. And what that means is that even very, very sparse models can perform as well as like the best black box models for tabular data sets. So like I said, while we're working with, while we're working on interpretable neural networks, which is obviously a task a lot of people are thinking about, including, my lab, which is working on interpretable neural networks for mammography, we have to realize that there are just tremendous opportunities for tabular data, but you have to really optimize these models well in order to get up to the accuracy of the black box models. Like if you want them to be really tiny and keep that accuracy of the black box models. Now, if we think about the history of predictive modeling over the last century, only a small amount of that time did we actually have data. So most of the predictive models needed to be created by humans. So when we think about, okay, what kind of predictive models do we want to build now that we have data, and we want these models to be interpretable to humans, we need to think about what types of models humans designed in the absence of data. And the most popular form of predictive model, hands down, was scoring systems. So a scoring system is a sparse linear model with integer coefficients. So here I've put up what's possibly the most widely used predictive model in healthcare, maybe this in the APGAR score, I don't know. But this is the CHADS2 score. It predicts stroke in patients with atrial fibrillation. Now this model is not a machine learning model. It's not even a data-driven model. It was designed by humans and validated on data afterward. Now, I should mention that scoring systems have been used for about 100 years. Okay, so this is a paper from 1928. It's a very famous paper by Burgess on the factors determining success or failure on parole. Now, here's how Burgess described the scoring system he created, where he gathered 21 factors that added, those 21 factors added up to, the score, okay? So he wrote, accordingly, 21 factors were selected, by which each man was graded in comparison with the average for the 1,000 cases upon the probabilities of making good or failing upon parole. So he did some really interesting statistics too, where he sort of, calculated the number of factors each person had, and then he translated that into a risk of non-violating parole, being a non-violator of parole. Okay, and that's what this table here is at the bottom. It translates the scores into risks. And then he also did some interesting kind of funky group level analysis where he grouped people into different categories of social type and then compute their violation rate. But some of these categories are pretty funny, so I couldn't resist putting them up on the slide. So it could be a ne'er-do-well or a mean citizen or a drunkard or a gangster or a recent immigrant, oh my goodness, or a farm boy or a drug addict. We don't do this stuff anymore. But what we do is actually very, very similar in terms of the actual analytics, right? So this is a more recent scoring system from the Pennsylvania Commission on Sentencing. And it's still the same types of models where you add up the points and that translates into a risk. Why are we using the same types of models? Because they're easy to use and easy to understand. Here is the Violence Risk Appraisal Guide from 2006. I'm going to zoom into that so you can read it. So here again, it's points. You add up the points, it translates into a low, medium, or high risk, and depending on your score. Here is, and in medicine, they have so many of these risk scores that they actually group them on these websites by specialty. So you can actually kind of scroll down to a specialty that you want and get all of the scoring systems for that specialty. So I'm going to scroll down here to neurology, and then I'm going to click on seizure risk, and then I'll click on the 2 helps to be score. And here is a page where you enter in some information. You just punch information into this like medical calculator, which is actually just a scoring system, and you get points that translate into a risk of seizure in the next 6 hours. The problem, of course, with all these scoring systems is that when you design them by hand or with heuristics, they're not very accurate. So of course, the question I'm going to be asking is how to design these scoring systems to have optimal predictive performance according to data, but also be understandable and easy to use by humans. The thing about the 2 helps to B score that makes it different than all of the other medical scoring systems is that it was not designed by humans or using heuristics. Okay, so I want to talk about this application for a while because this is actually really important. Okay, so let's say that you have an aneurysm in your brain and it bursts so that you have a hemorrhage, you have blood like leaking all over your brain, you have like a blood explosion in your brain. So this is like a brain hemorrhage. And what would happen to you is you'd be rushed to the hospital, you would get emergency surgery, and then you'd be placed in the intensive care unit with EEG monitors all over your head. And those monitors are detecting for the possibility that you might get a seizure or that you might have seizure-like activity. Now, seizures are common in critically ill patients. About 20% of patients get them. Seizures cause brain damage, they cause death, and doctors will do a lot to prevent you from having a seizure. They might even shut down part of your brain to prevent the seizure from sort of destroying that part of your brain. And now, these are not seizures where people physically shake. They're subclinical seizures, so everything is in your brain. So the only way to detect seizure-like activity is with EEG monitors. Now, these EEG monitors are, they're expensive, and there's never enough monitors, and there's never enough doctors to go around to read those monitors. And so people end up on the monitors for way too long, which deprives other people of monitors that they might actually need. So we really do need to predict seizures in advance to determine when we can take people off these monitors. So we created the 2 helps to B score, right? The same one that we saw in Medscape. That was us who designed it, and it's now widely used in hospitals, and it's small enough that it can fit on a PowerPoint slide. But it's also as powerful as our best black box machine learning models. And if you enter the information into the screenshot that we saw earlier, it will calculate the score just like this. Okay, so it's called 2 helps to B because it's 2 HELPS and then 2 points for the B. So the doctors can memorize the whole model just by knowing its name. And I know it looks like a rule of thumb, but it is a full-blown machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. It's just as accurate as black box models, and it doesn't force you to trust it, right? Doctors can decide themselves whether they want to trust it. It doesn't force you to trust it like a black box model. Doctors can also calibrate the score with information not in the database. There might be, unusual circumstances that might sort of cause a doctor to adjust how they care for the patient, and they might look at the patient and say, oh, that patient needs an extra point, so I'll give them an extra point. And also the score could be explained to non-physicians so that they can understand like why somebody's being taken off of CEG monitoring, for instance. All right, now I know it looks like it has only 6 variables, but those 6 variables were chosen from a database of over 70 variables. And everything here, like these thresholds, all of this stuff was chosen by the algorithm. Okay, so in other words, what I'm saying is that there's a combinatorial explosion in the number of models to choose from, right? You probably think this is all easy because the model looks so simple, but it's not, right? There's a bunch of really important challenges that you have to think about when you're designing these models, right? The first challenge is that you really want to maintain accuracy as compared to the best black box. You want it to have only a few terms, perhaps some custom constraints like fairness, and you want it to have integer coefficients like 1, 2, and 3, and not like 27 or something, right? We want the same thing as what people have been doing since 1928, so that you can compute all the counterfactuals in your head. Everything is just got to be, integers. Now, typical approaches for creating scoring systems are to just have humans go into a room and come up with the model. Okay, that's one typical way that people do things. Also, another popular approach is to use ad hoc techniques, so where you sort of manually select which features you're going to put into the model, then you run logistic regression, then you scale the coefficients, and then you round the coefficients. And that's what's been used for a whole bunch of different medical scoring systems that are out there. I call this fiddling with logistic regression. The problem is, these methods, they just don't work. They produce suboptimal scores, and they rely on humans to do high-dimensional constrained optimization. All right, so let me give you an example. So this is an elastic net model for the seizure prediction problem for just a few variables, but it's difficult to use. Like if the patient has prior seizure and patterns superimposed with fast or sharp activity, like these things, then how far is their score from 0? And what would need to happen to get their score to 1.6? Can you memorize this model and use it on a patient as you're dealing with a million other things? Probably not, especially if it has more variables in it. Okay, so let's try rounding the coefficients. So that didn't work. I lost almost all my signal, and my probabilities are a mess. Let's try again. This time, I'm going to scale all the coefficients by multiplying them by the best factor I can, and then rounding. This is, again, not very accurate, and it isn't really what I'm looking for. It looks better, but it's just not as accurate as the 2 helps 2B score. And maybe if I fiddled with it some more, I could get something better. But it would be really hard to get something as nice as the 2 helps 2B score. And fiddling is just not what we should be doing in this case, right? We should be actually formulating and solving an optimization problem to get the answer. Okay, so if computation was not an issue, what optimization problem would we solve? And I claim that it's this one. So in this optimization problem, there are 3 important pieces. The first one is the logistic loss here that's used in logistic regression, which keeps the model kind of risk calibrated and accurate. And then this term over here is a model size term, which says keep the number of terms in the model small. And then this set of constraints here says please make the coefficients small integers, so numbers between -10 and 10. So when we were designing the 2 helps 2B score, it could have chosen any number between -10 and 10, but it chose the 1, 1, 1, 1, and 2, right? That's just what came out of this optimization problem. Okay, so this is what we want, and you can add optional constraints too, like fairness constraints or false positive rate constraints, or whatever you want. Okay, so if you're an optimization expert, you might look at this problem and say, that is really hard. That's a mixed integer nonlinear program. And also you might see that like if you sent it into a MinLP solver, it could take till the end of the universe to solve it, right? This is actually a really hard optimization problem. But you can also see why rounding, when we formulate it this way, you can see why rounding doesn't work either. So let's just consider like, the logistic loss, which is convex. So it has like these nice kind of convex level sets here. And this is the logistic regression solution. And so let's say that you round the coefficients to the nearest integer. So you round to be on the integer lattice. So when you do that, you're going to get one of these solutions. And the problem with rounding here is that you're going against the performance gradient. You're actually losing a lot of performance when you did that. But if you actually optimized, you would find out that there's a good solution here that would be really difficult to find by rounding. And you could say, well, the way you've drawn it, you've drawn these long, skinny areas of low loss, and you might think that they're unrealistic, but it's not, right? And this is the reason for the whole field of mathematical programming, right? Most problems are like this, right? Roundings does not always get you where you want to go. And then also, like if you have constraints, those make the problem even harder because the rounded solution can easily violate the constraints. So you can see why it's actually useful to actually solve the optimization problem. And the solution to it gives us models like the 2 helps 2B score. So, after solving the problem, which I'll tell you how we did in a minute, we go back to 2 helps 2B, okay? So now when you have your aneurysm which bursts, you have your hemorrhage in your brain, You go into the intensive care, you go to the hospital, get surgery, go in the intensive care unit, get the EEG monitors placed on your head. Then the neurologist can now read the EEG and say, oh, this person has a 2 helps 2B score of 3 because they have this, this, and that. They're high risk, therefore I'm going to place them on continuous EEG monitoring for at least 72 hours and start them on preventative medication for seizure. Now, so far, 2 helps 2B has been validated on an independent multi-center cohort. This is not a study that I was involved with. This was done by the neurologists. And what they found was that it held up very nicely in validation. So this is predicted probability of seizure and true probability of seizure. So being on the diagonal is good. And then the initial study that we designed the model from is in blue. And then the validation study from the independent centers, medical centers, is in green. And you can see that these are very, right on top of each other, essentially, which indicates that the model generalized well to other institutions. Now, so far, 2 helps 2B has been implemented in several different hospitals, and it's resulted in a substantial reduction in the duration of EEG monitoring per patient, which, according to the doctors, allowed them to monitor 2.82 times more patients than before, which, according to them, helps them prevent brain damage and save lives. Now, I want to talk about the machine learning algorithm that produced 2 helps 2B, which is called RiskSlim. And it solves this difficult optimization problem. But before I tell you about RiskSlim, I need to tell you about cutting planes. RiskSlim is a cutting plane algorithm, but traditional cutting planes don't work. And I need to explain why before introducing RiskSlim. So I'm going to give you a short lesson on traditional cutting planes for those of you who don't already know it. Okay, so let's say that I'm going to minimize the logistic loss, which is convex. So if I was using traditional cutting planes, what I would do is, I'm minimizing this loss function. It's non-negative, it's convex. And the traditional cutting plane algorithm would start somewhere. So I'm starting it here. And it would calculate the objective and the gradient. So that's here. Then it generates a cut, right? This is a cut. And then this uses obviously the gradient it just computed. And then it would minimize the blue surrogate, which is going to be a piecewise linear function. But in this case, it happens to know that the objective is non-negative. So it's going to go here. Okay, and then we'll repeat. Minimize the blue surrogate. Again, we know the function's non-negative. Keep going. So now it evaluates the objective and the gradient, adds a cut, which is here. And then eventually it'll realize that it's found a solution because the minimum of the surrogate equals the minimum of the objective. Now, something goes wrong with this whole situation when creating models with integer coefficients. So let's show you where that happens. So if you're here in the computation, so you iteratively constructed this surrogate, when you minimize it, you end up here. And you can see that minimizing the surrogate involves a linear programming problem, right? Because these are lines here. But the solution needs to be at an integer because, we need to have points that are feasible. They're on the integer lattice, right? The coefficients are supposed to be integers. We're creating scoring systems here. And so what that means is that you have to solve a mixed integer program at every iteration and not a linear program. Now, this is a headache because mixed integer programs are much, much, much more difficult to solve than linear programs, right? And you have to find the point on the lattice that minimizes the objective. You need to solve that MIP also to optimality at each iteration, because otherwise you have no idea when you've actually solved the problem. And still, every iteration you're adding a cut. So as you add more and more cuts, the MIP that you have to solve to optimality gets bigger and bigger and bigger, and more infeasible by the second, and that's bad. So no matter how big or small the data set is, after you add 200 cuts, the problem becomes difficult for the solver and it totally stalls. So after about 70 iterations, so this is about 70 cuts, and the MIP just can't solve it. And it just took over 10,000 seconds to just solve even one iteration of this. And we just had to turn it off. It just stalled and said, I can't do it. So, and the optimality gap, which starts at 100%, it's supposed to go down to 0. It didn't even go down at all, right? So that's bad. So we designed a new cutting plane method that does not stall. Now with this new algorithm, at each iteration, instead of solving the mixed integer program from the surrogate, it solves the linear program, the LP, which is much, much, much easier to solve. Okay, so it gives you this solution over here. Okay, but what do you do with that, right? What do you do with that? Because you know it's not feasible. Okay, so, well, if the solution to the linear program happened to be on a feasible integer point, then the algorithm actually solved the MIP serendipitously, so it can add a cut. Okay, so that's one possible thing that could happen. You could sort of accidentally solve the MIP. But if it doesn't land at an integer point, then you know that there are no feasible solutions in this whole region. So you get rid of the whole area, and then you iterate separately in each of the two pieces, okay? So then again, we're gonna solve the linear program in each piece. Okay, so this time, okay, so we'll solve the linear program. So we solve it. This time, we can create a cut since the solution, it's just right on the integer lattice. And same thing over here. So we solve the linear program. We accidentally or serendipitously got a solution to the MIP, and we can add cuts, okay? And we could just continue to proceed like that by either subdividing the space by sort of chopping the problem into two pieces, or we add a cut at each iteration. And this algorithm completely solves the problem. So even if we run it for 10,000 iterations, the solver finishes in less than 100 seconds, and the optimality gap gracefully goes down towards 0. So we don't find stalling in this new cutting plane algorithm. This really completely solves the problem, and this is the algorithm that RiskSlim uses. And it provably converges to the optimal solution. All right, so let me repeat that just in case you missed it. So here we're optimizing logistic loss, subject to the constraint that we have to be on the integer lattice. We solved the linear program. We're happy that we did that because it only involves solving a linear program. So computationally, very nice. So we're happy about that. But then we realized that, oh, wait, our solution's not feasible because we have a non-integer coefficient. So then we're unhappy about that. So what we do is just block off this whole region, and we tell the algorithm, you're not allowed to pick any coefficients that you're not allowed to pick this coefficient to be, you have to split into two subproblems. You have one subproblem where the coefficient has to be less than or equal to 5, and the other subproblem where it has to be greater than or equal to 6. And so therefore it can't ever get any value in between. And so you just proceed like that. And if the subproblem leads to a feasible integer solution, you add a cutting plane. If not, you split it into two subproblems just like this. And then if the minimum of the cutting planes equals the objective value, then you know you've solved the problem. Now currently, LCPA is the only method that generates solutions to this problem within a reasonable time. MinLP solvers won't work. They could take until the end of the universe to solve even like for a moderately sized data set. And as I mentioned, standard cutting planes require solving larger and larger mixed integer programs, which very, very easily starts to stall. All right, now, after we developed RiskSlim, we weren't just going to use it on one problem, right? So we actually used it for a whole lot of different medical scoring systems. We developed a screening system for ADHD in adults. We also worked on sleep apnea screening and the clock drawing test. The clock drawing test is interesting. This is a test for Alzheimer's and dementia where people draw a clock with a digital pen and then they copy that clock. And then the very subtle movements of the person as they're drawing get recorded by this digital pen and are used in a scoring system to assess whether the person is experiencing some form of cognitive decline. Now, we also used it for predicting recidivism, so predicting whether someone will commit a crime after they're released from prison. And this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications. And so stay tuned for that. So the question that everyone keeps asking me is whether interpretable models are really as accurate as black box models. And now the way we answer questions like this in machine learning is that we compare algorithms by looking at benchmark data sets. So here's a great benchmark. This is the Explainable Machine Learning Challenge benchmark data set. It's a home equity line of credit data set, so you're trying to predict whether someone's going to default on their loan. Now, the data is from FICO. They gave us 10,000 loan applicants and a whole bunch of factors of their credit history, and we were supposed to predict whether they're going to default on their loan. If you run black box models on this data set, the best accuracy you can get is somewhere around 73%. Best black box AUC is somewhere around 0.8. Okay. Now, IBM, which won first place in the challenge, actually produced a really tiny little model with only 6 questions, but they broke the golden rule of interpretable machine learning, which was that they lost a lot of performance. So they lost a little bit of accuracy, but the bad thing is that their AUC went down from 0.8 to 0.62, and AUC ranges from 0.5 to 1. So to go from like 0.82 to 0.8 to 0.62 is not something that we would ever do. Whereas our entry, which won the FICO Recognition Prize, didn't lose any performance at all over the black boxes. So just to give you a little background, we didn't have access to a domain expert when we were designing this model. So we went to the FICO website and we saw it was all about neural networks. So we thought, oh, they want a neural network. So we designed a model that was supposed to look like a neural network, but it's actually just a bunch of little itty bitty tiny logistic regression models. It's like a bunch of little itty bitty additive models that use 1 to 4 features each. Okay, and then we combined those subscales into a final model at the end. So it's just 10 very simple subscales. I'm going to zoom into one of them so you can see it. This is the delinquency subscale, which is one of our biggest models that uses only 4 factors. Okay, so here's a prediction being made from the delinquency subscale. So it'll look at the person's percent of trades never delinquent. This person had a bunch of delinquent trades, so they get some points. Months since most recent delinquency, this person had a delinquency within the last 8 months, so they get some points for that. And then they get points for these things as well. The total score gets added to a bias term, which gets fed through the logistic function, and it translates into a risk of 79.8%. So this person has a risk of 79.8% chance of defaulting on their loan just based on their delinquency information. Okay, so literally that's all we did. We constructed a whole bunch of these additive models, like 10 of these little itty bitty tiny additive models like that, and then combined them all into a logistic regression model with 10 factors. Anyway, so that's what we did. So in any case, what we found was that even on challenging benchmark data sets, the interpretable model's accuracy is equal to the black box model accuracy. Okay. All right, now I want to get back to the topic of criminal recidivism and the COMPAS score. So as I said, this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications. Now, something you need to know here is that explaining a black box is not the same thing at all as creating an interpretable model, okay? So if you create a model to approximate a black box, that is an approximation, that is not an explanation. Okay, because the black box and the explanation could use totally different variables. Like you could have a black box and an explanation that are similar to each other, where the explanation depends on age, number of prior crimes, and the person's race, whereas the black box might only depend on age and number of prior crimes. And someone might take the black box, approximate it by a linear model that depends on race, and say, oh, the black box depends on race. And you could say, well, this sounds silly. Like nobody would ever do that. This is, nobody would ever do that. But the truth is that that actually might happen. And it actually did happen. And it happened with COMPAS. And that is exactly what happened in the very famous ProPublica article that everyone always talks about. So this is exactly what they did. They approximated COMPAS with a model that depended on race, and then they concluded that COMPAS depends on race, in addition to age and number of priors. Okay, so let me just give you a bit more detail about what they did. So first, they showed that the false positive rate and false negative rate of COMPAS varied by race. And then they suggested that this might not be a good comparison because we should include age and number of priors and re-examine. Because the thing is that age and number of priors are correlated with race because of systemic racism in society. So those correlations don't necessarily imply that that COMPAS depends on race, right? You have, because the populations of blacks and whites in the database were very different. The blacks tended to be younger and have more prior crimes due to systemic racism in society. So what ProPublica did to remedy this was they included age and number of priors into their model, their approximation model for COMPAS. And they still found that their linear approximation to COMPAS had a low p-value for the race covariate. So then they concluded that COMPAS depends on race. So what happened here is that I don't think COMPAS is linear, and so their conclusion that COMPAS depends on race doesn't work. All right, so let me show you why ProPublica's assumption was particularly bad. So we took the data from Florida that was used in the ProPublica piece, the COMPAS data, and we plotted it. So what I'm showing you is a scatter plot of COMPAS violence score versus age. And as you can hopefully see here, there was a really sharp cutoff of COMPAS scores for each age, right? Like if you're 20 years old, you're not going to get a COMPAS score of -4, right? That's not going to happen, okay? So we think that these might be the minimum COMPAS score for each age, right? There's a few outliers, right? Maybe a few typos in the database, but overall not pointing to a linear function of age. And, it looks like COMPAS depends heavily on age here, right? And so if they messed up age, that could definitely mess up their analysis. Like I can't find a linear function of age that could really work here, okay? So what we did was we took the COMPAS score and subtracted this function of age, right? We subtracted that out and then tried to figure out whether the remainder depended on race. So we sort of, hopefully, we included kind of a good enough approximation to how COMPAS depends on age. Take it out. Let's see if COMPAS still depends on race. And it didn't seem to. We ran machine learning methods with and without race to see if they need race to predict COMPAS well, and they perform similarly. So race does not boost performance, just like in our interpretable recidivism paper, and ProPublica's conclusion is pretty shaky. So then if race doesn't actually appear in COMPAS, other than through its correlation with age and criminal history, then how did they find these pairs of people, right? These examples were key evidence on how COMPAS depends on race, right? Because the white person had a longer criminal history, right? This white person had a longer criminal history and a lower score than the black person. The thing is that if you look at these two people, right, the black person is much, much younger than the white person. So if COMPAS depends heavily on age, that could explain how this happens, right? Vernon Prater is old, so he doesn't get the age points. And I'm not saying that I agree with this, but if they had compared two people with the same age, then it would be much more convincing that COMPAS depends on race in addition to the strong dependence on age. So ProPublica's claims not really holding up with respect to race, right? COMPAS might not actually depend on race other than through its correlations. But I think there's a much worse problem with COMPAS that ProPublica completely missed, which is that humans are not very good at inputting data reliably, which is what caused the issue with Glenn Rodriguez. You've got 137 factors entered by hand for each survey. If there's even a 1% error rate on that data entry, there's a 75% chance of at least one typo on a survey. And this is a serious disadvantage to complicated or proprietary models, especially models that determine people's freedom, right? And like I said, this is exactly what happened with Glenn Rodriguez with the COMPAS score. So we were looking at the Florida data to try to figure out like how often these typos might happen. And we found some strange inconsistencies in the data. So these are people with the lowest possible COMPAS violence decile scores. So these people have COMPAS score of 1, so 1 out of 10. They're the lowest risk category. And look at their criminal histories. I mean, some of these people have like, battery on a law enforcement officer, attempted murder in the first degree, aggravated battery with a deadly weapon. I mean, how could this possibly happen that these people would get the lowest possible risk for violence? Like, there's no other way I can explain this other than a data issue. That's just the tip of the iceberg. Here's people with COMPAS scores of 2 and 3. So again, low risk individuals with very, very extensive criminal histories, robbery, with a deadly weapon, kidnapping, solicit to commit armed robbery. I mean, it's just, how could they possibly get such low COMPAS scores if it weren't for typos? We even think we found typos in the COMPAS documentation from North Point, right? North Point claims that, North Point's the COMPAS designers, right? They claim that COMPAS has a linear dependence on age, but we obviously think that there's a nonlinear dependence on age. So anyway, we published an article attacking both ProPublica for explaining a black box model wrong and COMPAS for being a black box where typos cause decisions, which of course makes us very unpopular with both of them. And we published it in the Harvard Data Science Review. And the editor of that journal, the famous statistician Zhao Meng, solicited a whole bunch of commentaries on our paper from famous criminologists and legal experts. And one of these commentaries was from the company that makes COMPAS. And they wrote an absolutely scathing article saying that COMPAS is interpretable, which is pretty funny because if that were true, it would have saved me and ProPublica a lot of trouble. But in the mountain of criticism there, they admitted a couple of things that were super interesting. They wrote, the authors, so us, have taken a clearly informal description of the violence score in the practitioner's guide, but it was an equation. You can't get more formal than an equation. Anyway, they wrote, it was not intended to be a technical document. Discussions of appropriate variable transformations are beyond its scope, and we note that the skewed age variable is an ideal candidate for a normalizing transformation. A sort of like a, kind of like a subtle admission of guilt there. And they also had a section of transparency in their paper where they said saying that they were pursuing copyrights for these formulas, and we were like, whoa, maybe we'll actually make a difference here. All right, so just to summarize, scoring systems are good when you optimize them carefully, and typos are bad, which happens more often with complicated or black box models. And evidence suggests that we don't need such models in the justice system. All right, so just to wrap up, I wanted to tell you about the problems that we are working on in my lab right now. So you've heard a lot about scoring systems. We have a new paper on something close to scoring systems, which is generalized additive models. We have a new paper in AI Stats 2022, which has been posted, I believe, today, or maybe it will be on archive tomorrow. We also work on data visualization using dimension reduction tools, where we take high dimensional data, project it down to 2 dimensions to try to preserve its structure so that we can see what is in the data. So this is a mammoth that has been projected from 3D onto 2D, kind of crushed like a leaf there. And then I co-run a lab on almost exact matching for causal inference. So this is the problem of trying to match people from a treatment group to people people in a control group so that you can mimic a randomized control trial using observational data. And we want to match people as exactly as possible so that everything's interpretable. And then I also work on optimal sparse decision trees. We have a AAAI paper that's going to be presented tomorrow on that topic. And then we also work on interpretable neural networks for computer vision with application to mammography. And then finally, we work on understanding the set of good models and the importance of variables, because often people don't just want one model spit out by a machine learning method. They might want a whole lot of good models, and they want to be able to choose from those models. So that's what we're studying there. All right, thanks very much.
Thank you, Cynthia. Great talk. And we have plenty of questions. So the first one is the more generic one. So we'll start with that one. So is accuracy the right way to measure the criminal justice domain? Wouldn't false positives or false negatives precision trade-off be more important? Or in other words, should we have a person in jail that is innocent, or we should free a person that's a criminal?
Yeah, so I just presented accuracy to keep things simple, but we actually do present true positive and false positive rates in our paper. And you know, the result that I showed you where I was saying, you know, we're just as accurate as COMPAS, we have almost exactly the same true positive rate and false positive rates as COMPAS.
Great. So there's another question that you use the same type of models. Can it pose to be a problem when referring to will it pose to be a N of 1 trail problem? This is by Rinal. It's all of them are in the chat.
I don't understand that question. Use the same types of
Yeah, there's some typos there. So let's go to the next one. So
Yeah,
for the feature model, how is this different from building a black box model like a BDT, using data and then performing a feature importance analysis with something like Shapley values and then choosing the most important features?
So you can do that. Like, that's one way to do it. But you wouldn't ever want to use GBDT and just say, well, I think the most important features are this, this, and that. Like, you really want the doctor to memorize the model for these like super high stakes decisions. So I think this question's getting at something else here. Let me just read this carefully here. Once that's done, one can assign scores to the features based on their importance and then assign probability to the scores based on the black box model. But then you still have the black box model, right? So the problem with the black box model is that if you have some input error, like if one of the features is input wrong, then the black box model produces something, and then you know, you don't really know exactly what was wrong unless the Shapley value says, no, it was that feature that caused the problem. So, I mean, look, Shapley values, they just tell you which features are important. But in my models, I know which features are important. And my models are just as accurate as any black box you can construct on that data set. So I know that it's like super popular right now to just build a GBDT and just say that you know which features are important. But it just doesn't tell you what is going on with those features. You can't compute counterfactuals in your head. You can't track errors nearly as easily as if you could memorize the model. And I'm not losing any accuracy over the black box. So, you know, I view mine as strictly better than you know, using a black box with an explanation. I know, like I said, I know that's popular right now, but I don't think that's the right way to solve the problem.
Right. Chandra has a related question. So in 2 helps to be, how do doctors remember the risk percentages? Or they just say any score above, say, 3 is bad? In which case, could you come up with simple scores?
Yeah, so they don't have to memorize the percentages. All they need to know is what to do given the score. So in other words, if they know the person has a 2 helps 2B score of 3, they know they have to put them on monitoring for at least 72 hours, right? They don't even need to memorize those risks. They just have to memorize the policy, like what should you do in this case? And that's something they can memorize.
Yeah. Another question from Ian Paul says, isn't risk slim just finding the flaw and ceiling of the initial linear programming solution? Or is this just for this example, there are exceptions to this?
No, RiskSlim doesn't find the floor and ceiling of the initial LP solution. So once the LP is solved, then if it's not at an integer point, then it'll do like it'll do branching, right? It'll branch like a branch and bound problem. And then it'll solve each of those 2 subproblems separately. So it's not computing any, you know, I mean, it's computing, right? It's computing, like if you get 5.5, it'll say, give me a solution less than 5. And then it'll say, give me a solution greater than or equal to 6. And so you get both of these possible options accounted for.
I will leave Osama's question to the end because it's for the end. So any comments on how the dimension reduction techniques are different from standard techniques like PCA or TSNE?
Yeah, so Pacmap, this is the latest technique that we've designed. So Pacmap is a competitor for PCA and TSNE. So PCA doesn't, PCA, I'm glad you gave these two examples here. PCA does great for preserving global structure, like it kind of puts the points in the right part of the space, but it does terribly for a local structure. PCA just sort of puts everything in blobs. Like if you ever PCA MNIST, then it just sort of produces a blob. Whereas TSNE does local structure wonderfully, but it does global structure very poorly. So if you do TSNE for MNIST, it can divide some of the clusters that should be one cluster, it'll divide them into two clusters and put them on opposite sides of the plot. So our method, which is, again, it's called Pacmap, it handles both local and global structure at the same time, and it's much simpler than TSNE.
Thank you. So can you tell us the trade-off between data size and model accuracy for your approach? What if the data set is small? Does it still perform well?
Oh, okay. This is a question from Joe. Hey, Joe. So the it's not clear that there is a trade-off between data size. So data size and model accuracy.
Yes. How much data you have? That's matter.
I think it's a different type of trade-off that's more important. I think it's a level of noise. I think if the data is kind of noisy, then you can get interpretable models more often. Like, for example, predicting criminal recidivism. Like there's no way you can deterministically predict whether someone's going to commit a crime in 2 years. Like there's a lot of like random factors that go into that. Did the person get a job? Who are they hanging out with? You know, maybe they committed a crime, but they weren't caught. You know, all these types of things add randomness. And that extra randomness actually kind of smooths out the hypothesis space. And so you're able to get interpretable models more often. And it also reduces accuracy as well. So, you know, there is a trade-off there, but there's no sort of general hard, fast rule between amount of data and sort of accuracy, right? You can have large data sets, low accuracy, large data sets, high accuracy, and sort of vice versa. It just depends on the problem.
Before going to the last question, because we're almost on time, let me remind you, all of you, about our 2 series, the expeditions, coming next month, and also the next distinguished speaker that will be Gina Vince on clinical decision making. So will be related to some things that Cynthia have said. And the last question from Osama. So what would be the takeaway lesson regarding what is it that the complex, like a black box, is actually justified, and how do we thematically avoid overcomplication?
So I think black box models are totally fine if you're doing a low stakes decision, right? If you're doing advertising, if you're doing like detect a cow in an image, right? Who cares about interpretability, right? The only time you need interpretability is when there's something bad that would happen if the model went wrong. And there's another case where you don't need interpretability either, which is when the human can check every bit of the calculation. So if you have like a deep learning model that does segmentation of the heart chambers, for instance, you don't need interpretability for that because a human can just check it afterward that the segmentation was correct. So I think you know, there are cases, lots of cases where black box models are perfectly happily justified. In terms of thematically avoiding overcomplication, I think we need to regulate some of this stuff. Like, you know, from what I've seen, like from the articles that I've seen, you know, I think for some of these high stakes decisions, you've got companies who are selling these models at the expense of people's freedom. So, you know, I think for kind of very important decisions, then we should regulate that no black box model gets used unless you can prove that there's no equally accurate interpretable model. And then in that case, if my prediction is correct, then we'll always use interpretable models for those types of problems.
So to complement that and to finish this wonderful talk, is, in your personal opinion, because I know this is a hard question, what is worse, a false positive or a false negative in COMPASS, like, for example, it's a specific case of COMPASS, or that will depend on the data of each case?
Yeah, I mean, I'm not a criminologist, so I can't really answer that question, and I think it depends on the type of crime, right? So, like, you would not want to let a murderer just sort of walk around the streets and just be granted bail, right? But at the same time, if it's someone who is just, if it's like a misdemeanor, some smaller crime, then it would be bad if that person was a parent and couldn't take care of their child because they got stuck in prison because of a miscalculated compass score. So, I think it just depends on the situation.
Yeah, and would it imply that when maybe we need to set different models for different types of crime, or not just a single one?
Yes, and in our interpretable recidivism paper, we had predictions for many different types of crime in there.
Great. Okay, thank you, Cynthia. This was a great talk, and I hope many people see the recording later. Thank you.
Thank you.